Okay, so today we're going to be learning about linear, linear first order differential equations. So as we've seen previously, we have seen first order differential equations. It's just they were separable. Okay, we could get each part to the left and the other variable to the right and integrate both sides and solve that way. We won't be able to do it with these ones, so we've got another technique, and these types are called linear. Okay, so that's the key difference there, the word linear. Alright. So linear differential equations take the form dy by dx plus some function of x, we'll call it p, multiplying the variable y, and that will equal a different function of x, we'll call q of x. Okay, so we've got two different functions in our formula there. We've got dy by dx plus some function p of x multiplied by y equals q of x there. Okay, so we can't separate them because we've already got functions of x on each side. Therefore, this takes a different format. They're called linear. Okay, so just to make a wee comment, we are p of x and q of x are functions of x. Okay, and x only. All right. So we're going to have to introduce a new terminology now in order to solve these. Okay. So to solve this type of equation, we have to multiply all terms by a factor, and it's called the integrating factor. Okay, we'll just highlight there the integrating factor. Okay, so that's the thing that's going to be new for us. Okay, and we're going to note it. So denoted. Any of these signs you might recognise that symbol. That's mu. Okay, it's a Greek letter mu. Mu of x. It's like a U with a sort of tail at the start. Okay, mu of x, which converts the whole left-hand side of the equation into the derivative of a single function. Okay, so that's what it's going to do. Okay, all right. Don't worry too much about that last statement regarding why that happens. Okay, just more for the fact that these questions require an integrating factor, and that's the first step in solving these. Okay, and you'll see how the integrating factor will allow us to solve. Maybe we're trying to solve for a function y that satisfies the equation. Okay, that is our end game. We solve differential equations. Okay, So I better tell you how we're going to work out the integrating factor. So mu of x all the way. I do indeed. You've told me, no problem. Thank you, bye. I snap that out. So what we do is we take the exponential, but we integrate the function p of x on the top of the integral of the exponential. Okay, so we take the exponential of the integral of p of x dx. Okay, remember p of x was our function that was attached to the y, wasn't it? Okay, so we're going to integrate the function that's attached to the y and put that as our power of the exponential. Okay, that's what mu of x becomes. Okay, so how we then solve this equation? Okay, so once we get our integrating factor mu of x, then we multiply everything by mu of x. So mu of x dy by dx plus p of x mu of x y equals q of x mu of x. Okay. And remember what I said, it becomes a differential of the equation, doesn't it? There, up at the top, so therefore that becomes d by dx mu of xy, okay, which equals mu of x q of x. Because we want to solve for y, if we integrate both sides, we're going to get mu of xy. Oh, let me try that again. Mu of xy equals the integral of mu of x q of x dx. Okay, so that's how we go about solving for y after we find the integrating factor mu of x. Okay, it becomes mu of x times y on this left hand side, and then we integrate our function q of x, which is on the right hand side, but we multiply it by mu of x first, then we integrate it, then we solve for y after we do the integration. Okay, so that's how we go about solving it once we've found mu of x. Okay, you don't need to do these steps every time you solve it. I'm just showing you that's how you get to that. That's, if you remember that, you just go straight to that step after you found mu of x. Okay, okay with that? Okay, let's look at an example. Once you see a couple of examples, you'll then see how it works as opposed to that. There's a lot of stuff there. So we'll look at a couple of examples. So example one. Okay, so we're going to find the general solution. We're going to find the general solution of dy by dx plus y over x equals 1. Okay. So hopefully you can see that's not a separable form of our equation, okay? What we have is we've got the same thing, we've got a function attached to the y after the dy by dx, and we've got a function q of x, which is on the right hand side here, okay? So what I always write down is get your data. I would say, okay, so p of x, that was always the function that was attached to the y, so in this case is 1 over x, okay? Q of x is always the function that's on the right hand side, which is 1 in this case. Now mu of x, that's what we need as an integrating factor. So it's the exponential of the integral of p of x dx. Okay, so I need to integrate p of x dx. Okay. P of x is 1 over x, so that's going to be the integral of 1 over x. Okay. That's one of our standard integrals. That's one that's on our formula sheet. If we integrate 1 over x, we've seen that a few times, log x. So we get the exponential, not of the integral anymore, we've actually have integrated it. Let me change that. So we get the integral of log x. Okay, we don't need a plus c just yet because we need to integrate the right hand side later on. So what happens if you take the exponential of log x? You end up with x. Yeah, the exponential logs cancel out. So our integrating factor this time round actually just becomes x. Okay, the exponential log have cancelled. Okay, so if I want to put into my formula or put into my equation how to solve for this, okay, remember it was mu of x y. That's going to equal the integral of q of x multiplied by mu of x dx. Okay, so that's what I'm needing to sum these values into now. Mu of x is x, so that's going to be x times y. That's going to be the integral of q of x. Q of x is 1 multiplied by x dx there. Okay. So again, if I have x multiplied by y, if I integrate this, that's just x there. Integrate x, you get x squared over 2 plus c. Okay, this is a general equation, so we're going to have a constant. So we want to find the equation for y, so if I divide everything by an x, I'm going to end up with x over 2 plus whatever the constant was divided by x there. Okay? And if I had data, I'd be able to find what that constant would have been. But because I don't, it's the general solution, but my function would have looked like that. That would have solved the equation. Okay? Are we okay with the steps from there downwards that you can see on your page? Any questions? No. Okay, so that's the first example. The functions were quite nice, but it just showed you all the steps. Okay, you get your integrating factor, and then you use that to help you rearrange and solve for y. Okay, we'll look at a second example, and we'll try another one here. Okay, so let's go for example 2. Find the general solution of, so this will be x multiplied by dy by dx plus x minus 2. Oh, sorry, not fraction. Change that fraction. Multiplied by y equals x cubed. Okay. So here you can see it's linear. We've got a linear term y here. We've got a function attached to the y. We've got a function attached to the right hand side of the equation as well. So I can see p of x, q of x. Well, I could, but there's something that's not quite matching the form it should be. It should be dy by dx, shouldn't it? Yeah, not something multiplied. So I need to divide everything by an x here to get dy by dx. That's how it needs to look. So if I divide by x, therefore I'm going to get dy by dx plus x minus 2 over x y. If I divide x cubed by x, I get x squared. Okay, so that's now in the right format. I can now find what p of x is and what q of x is. Okay, I'll just run off the page there and put it back up. So again, p of x, that's the function attached to my y function. Q of x, that's the function on the right hand side, so that's going to be x squared. And I can now work out my integrating factor mu of x. So that's going to be e to the integral of p of x dx. So that's going to be e to the integral x minus 2 over x dx. Okay. If we divide both those terms by x, that's going to become e to the integral x divided by x is 1, 2 divided by x is 2 over x, like that there. Okay, 2 over x. And now I can actually integrate both of these terms. Okay, so if I integrate 1, I get x. If I integrate negative 2 over x, I get negative 2 log x, like that there. Okay, So I can tidy this up, even though I have integrated it, I can tidy this up. I'll put this off a page again, let me go back. So I can split the integrals up, okay, like what we've seen before. So that means that I would get e to the x multiplied by e to the negative 2 log x. That becomes e to the x multiplied the negative 2. Well, the 2 can go up as a power first of all. Okay, so that can be e to the negative log x squared. Okay, so remember we can move the 2 up to a power when it's a log. And if I rewrite that a bit nicer, if I put the negative now up as a power negative 2, it would be log 1 over x squared like that there. Okay, so that negative can go attached to the power negative 2, so it's negative 2 goes down as a fraction. Okay, power positive 2 on the bottom. Okay, e and the log cancel out, so I'm going to get 1 over x squared e to the x. Okay, so that's what my integrating factor mu of x looks like there. Okay, 1 over x squared e to the x. Okay, a bit nastier than say the last one we see. Okay, but you'll see it still does help us work out. So let's go back up and try and solve this now. So our format is mu of x y. That equals the integral of q of x mu of x dx. Okay, mu of x is 1 over x squared e to the power x y. I need to integrate q of x. Q of x was x squared, so it's going to be x squared multiplied by 1 over x squared e to the x dx. Okay, and you can see something quite nice happens on that right hand side. We do actually end up cancelling the x squared and the 1 over x squared, so all I'm left with on that right hand side is the integral of e to the x dx like that there. Okay, so that did turn out to be quite nice. If I integrate this now, so 1 over x squared e to the xy will equal e to the x plus my constant c. Okay, therefore, if I divide both sides by e to the x, okay, because I want to move this stuff over the other side. So if I do divide both sides by e to the x, then I'm left with 1 over x squared y equals, well, e to the x divided by e to the x is 1 plus c over e to the x. Okay, and then if I times both sides by x squared, I'm going to get y equals x squared plus cx squared over e to the x. Okay, so just because our functions were a bit more involved, it meant that we had just a bit more tidying up when we'd done them. However, the steps were the same. Integrating factor, and use the integrating factor in to solve and get a function of y. Okay, and again, general solution because we didn't have data, we couldn't find the value of c. But that's what that function would have looked like if we had it as a general solution. Are we okay with that example? So a bit more involved, using our log rules, exponential rules, but doing that one. Okay, I'm going to show you one last example, and that's going to be a particular solution one, so you can see just how putting data in can find the constant again. But after that, the rules also apply. Okay, so final example of the video. Example 3. Find the particular solution of dy by dx plus y equals 2x plus 4. Okay, given that when y equals 1, y equals 1 when x equals 0. Okay, so when x is 0, y is 1. Okay, So, start ourselves off, let's get ourselves our functions that we're going to need. So, p of x, that's the function attached to the y. Well, that's just 1. We've only got a 1 multiplying that y this time round. Q of x, that's going to be what's on the right hand side. That's going to be 2x plus 4. Okay, so mu of x, that's going to equal the exponential of the integral of p of x dx. So that's e to the power, the integral of p of x, which is 1 dx. And if I integrate 1, I just get x, so I'm going to get e to the x. Okay, that's what my mu of x will become there. It's just e to the x. Okay, so using that, mu of x y will equal the integral of what was it, q of x mu of x dx. So that's going to be e to the xy integrating q to the x, well that's going to be 2x plus 4 multiplied by e to the x, and that's what I'm left to integrate. Okay, so I put my data in there. So at this point here, anyone familiar with what we're going to have to use to integrate that there?
We need integration by parts.
Fantastic. You have integration by parts. I've got two different functions there. I've got 2x plus 4 as a function, and I've got a to the x as a function. That's going to be integration by parts. Okay, so that's what that's led us to do. So if I make u 2x plus 4, if I differentiate that, the reason why I picked that one as my differentiate one is because the power will decrease. That just becomes 2. If I make my v prime e to the x, well, if I integrate e to the x, I just get e to the x there. Okay, so that's going to be uv minus the integral of vu dash dx. U times v, that's going to be 2x plus 4 multiplied by e to the x. Subtract the integral of vu dash, that's going to be 2 lots of e to the x dx. So that's going to equal 2x plus 4 e to the x. If I integrate 2 e to the x, e to the x stays the same, so it's negative 2 e to the x plus c. Okay, so I had to use integration by parts there to integrate our right hand side there. Okay, so we can rearrange this just now if we wish, or we can put in the data just now. I'm going to go by putting in the data, so when x is 0, y was 1, that's the data we're going to use to find the value of c. So let's put that into our equation. So I'm going to get e to the 0 multiplied by 1 there. That's going to equal 2 lots of 0 plus 4 e to the 0 minus 2 lots of e to the 0 plus a value c. Okay, so I put my x and y values into my equation. So on the left hand side I'm going to get 1, that's going to equal 2 times 0 is 0, so I'm going to get 4. Subtract 2 plus c. Okay, remember e to the 0 is always 1, f to the power 0 is 1. Therefore that will tell you that c had to be negative 1. Okay, you would work that out, c equals negative 1. So therefore my equation now looks like e to the xy equals 2x plus 4 e to the x minus 2 e to the x plus c, which is now negative 1. Okay. Last step, let's get y, so we'll divide everything by e to the x. So therefore I'm going to left with 2x plus 4 minus 2 minus 1 over e to the x. Divided everything by the x, a lot of e to the x's cancel out. And if we just do one final tidy up, I'm going to get 2x plus 2 minus 1 over e to the x. Okay, so just that last step, we had to just put in a bit of data to find our constant. Apart from that, all the steps remain the same, mu of x, and then we had to then put it into an equation to solve. Sometimes you'll get integration by parts, sometimes it could be substitution might help you, sometimes it could be partial fractions, it depends on what functions, but all the skills we have, they're the steps that we require. Okay with that? Yeah.